Hello everyone, welcome to you in Pune University. My name is Dr. Manish Singh and I am Associate Professor in Mechanical Engineering Department. And this is video lecture series on basics of mechanical engineering, and this is lecture number 5 of unit 1. And in this lecture I am going to discuss with you melting practices and casting defects. So this is the content which I am going to deliver in this lecture. And after completion of this lecture, students are able to understand the functioning of cupola furnace for melting cast iron, calculate the charge quantities to be used in the cupola furnace, identify different types of furnaces used in the foundries, and students will also learn what type of defects produced in the casting process and what are the remedial measures. Let's start with the melting practice. Melting practice is a very essential for the metal casting process because in a metal casting process we need a liquid metal for the casting, is it right? And liquidification takes place in the furnaces. So many types of materials are used for the casting, therefore for their material and their type we choose the different types of furnaces, like we have a pit furnace, open heart furnace, rotary furnace, cupola furnace, and etc. So many types of furnaces are there. The choice of the furnace mainly depend upon the amount of metal required or a rate of melting required or rate of the casting we produce, and obviously it also depends upon the nature of material, because some non-ferrous metals are generally having low melting temperature, while as ferrous alloys are having more melting temperature. So according to their melting temperature we can select the different types of furnaces. So this is a cupola furnace, you can see this figure. This is a cupola furnace, and in this we have many sections, like you can see here. This is upper portion of the cupola furnace, and this is a cell whose height is very high, and obviously inside this cell we have a brick lining which act as a refractory material which prevents the conduction of the heat out from furnace to the outside. And inside this furnace initially we just fill a charge which includes calcium carbonate and the iron ore and other some mixtures, correct? And after mixing and yes, of course, we along with this we also add some coal which primarily used as a energy source. After mixing properly we just put this charge inside this furnace, and when now after that we just start firing. And once you fire the charge which is already available here, once you fired it, then because of this firing the coal burning start takes place. And of course the along with this burning of the charge, since in this we have a calcium carbonate, so chemical reaction may also happens, which and because of that all the impurities whose obviously weighter than the heavier than the liquid metal get settled down at the bottom of this furnace, and rest whatever liquid metal is available, it is just available here, and we can remove this metal from the by opening the wall. And of course along with this uh, along with this pure melted metal and the slag, several gases may also produce, and those gases may move upside, and those gases may also collected, and that can be further used for the electricity generation, is it right? So this is a basic cupola furnace, so you can read properly, everything is written here. Like you can see, this is a stack zone where all the charts we just filled properly, and this is a preheating zone where the preheating takes place, and this is a melting zone where the entire charge get melted, and this is a superheated zone where excessive heat is applied. And after that the coke or slag can coke is removed from this, and the slag can remove from this, and the molten metal gets settled down here, and this molten metal can be collected through this. And impurities, some impurities which are present whose weight is higher than the metal get settled down at the bottom, and that can also be removed like this, is it right? So this is a basic cupola furnace. So you can see cupola consists of a cylindrical steel cell with an interior line with a heat resistance fire brick, is it right? So fire brick basically used to prevent the melting of the cell of the cupola furnace, correct? And it consists of drop door at the bottom, after closing which proper sand bed could be prepared, and this sand bed provides the necessary refractoriness bottom for the molten metal. Here refractory bottoms we will make. And immediately above the sand bed in the metal tapping hole, which is initially closed with the clay tapping, and above the metal tap hole, normally in the position opposite to its slag hole, through which the slag generation during the melting process is trapped. Okay, so basically here we have a slag trap through which we can trap the slag. And of course, after the completion of melting and purification, we separate all the slags from this by opening the valve. And the molten metal can also remove from this by removing this plug. Is it right? So from this cupola furnace, we can extract pure metal as well as a slag, and we also collect some impurities. Then we also collect some gases which are further used for the as an energy source for electricity generation in a captive power plant, which is available in the steel making company or ore making industries. Okay, above the slag hole in the wind box, which is connected to air blower. Air blower is provided so that for the combustion we sufficiently we provide the oxygen, because without the presence of oxygen combustion does not take place. So sufficient oxygen is necessary, and therefore here we provide a air blower. The air enter the cupola through the tires a little above the charge platform and charging hole in the cell, from where the charge consists of a combination of pig iron, scrap iron, coke, and fluxes, correct, and the refractory lining. And next, here we have various zones in the cupola furnace, like well, the space between the bottom of the tire and the sand bed inside the cylindrical cell. The cupola is called as well, and actually this well collects all the molten metal produced during the melting of the charge by, and it is collected by just opening the tap. Okay, next, combustion zone. Obviously this is a zone where the combustion of coal takes place, and hence a huge amount of heat is liberated, around 1540 to 1870 degrees centigrade, and that heat is further utilized to melt the ore, so that the metal can separate from the ore and rest of the impurities get collected. Okay, and these are the some reactions that can happen during the heating of the ore or heating of the ore. Okay, like carbon react with oxygen produces carbon dioxide, and it will produce heat. Similarly, silicon react with oxygen produces silicon oxide, and it will also produce heat. And similarly, manganese react with oxygen produces manganese oxide. So whenever they form, then they always liberate energy. Next, reduction zone. Reduction zone of the cupola is also known as a protective zone, which is located between the upper level of the combustion zone and the upper level of the coke bed. And in this zone, basically CO2 is changed to CO through an endothermic reaction. And obviously, when CO2 react with carbon, that is coke, converted into carbon monoxide, then it will liberate a huge amount of energy. Is it right? And that energy is further utilized for the melting and for the chemical reaction of the process. And nitrogen does not participate in the chemical reaction occurring in this zone, as it is also other main constituent of the upward moving hot gases. Because of reducing atmosphere in the zone, the charge of protecting against oxidation, yes, whatever slag will form, which is collected over the molten metal, and this slag may act as a it provides a protective atmosphere to the molten metal, so that metal cannot make oxides. So slag, the purpose of slag is to it act as a protective atmosphere for the molten metal, like in a welding process. Next, in the melting zone, the metal get melted by using the heat, and in this the chemical reaction again takes place, like iron and carbon monoxide react with produces iron carbide, and this is a carbide plus uh, CO2 gas. Is it right? And next, preheating zone. Obviously, in the preheating zone, the charge is initially preheated so that easily combustion takes place, and it is heated around 190 degrees centigrade. And next, stack zone. The empty portion of the cupola have the preheating zone is called stack. Why it is called empty zone? We make this empty zone so that all the hot gases can be collected at the top of the furnace. because gases have low density, low weight, therefore it will be floating and over collected over the top of the furnace. Okay, and after that cupola furnace, let's see another furnace like crucible furnace. Okay, so this is a crucible furnace. Actually, in the crucible furnace, basically we use fuel like a diesel or a gas as a fuel. Is it right? Diesel or a natural gas as a fuel. So when you pass this a mixture of air fuel, then obviously here combustion takes place. So around this we have a hot gases, and by the hot gases, this is a ceramic crucible. This is a ceramic crucible, and this is a lid, which is nothing but this is also made up of ceramic, which act as a cover. Is it right? And this is a crucible which is also made up of a ceramic, and in this ceramic you just put the metal which you want to melt. Is it right? Like generally it is used for making non-ferrous alloys. So here brass is filled, and now when you start this furnace, then because of this hot flue gases, the metal get heated, and once the metal get heated, then with the help of tongue you just remove this crucible and use this liquid metal where you required. Is it right? So this is called as a crucible furnace. Is it right? So why it is called crucible furnace? Because in this we have a crucible in which we collect the metal, and the metal is indirectly heated with this heat produced by the air fuel mixture. Is it right? And obviously after combustion, the hot flue gases may remove from this, and these gases may further utilize for the steam generation or further other application, or after cooling we just release this flue gases into the atmosphere. But for this we generally use draught, so that the temperature and the carbon dioxide and carbon quantity of carbon dioxide will reduce. Okay, so this is a smaller foundry generally preferred for the crucible furnace. If you have a smaller foundry, then generally they prefer crucible furnace, and the crucible is generally heated by the electric resistance or gas flame. Is it right? It may be so. If it is electric resistance heated, then mostly we use induction furnace, correct? So which we can melt the metal. Otherwise, gas is also used for the melting, and along with gas, diesel can also be used, correct? So in these, the metal is placed in a crucible, refractory metal, and the heating is done to the crucible. Thus, there is no direct contact between the flame and the metal charge. This type of melting is very flexible since it is suited for a variety of casting, and its even melting rate is also very fast, correct? Melting both, we get very fast melting. Is it right? And degassing and metal treatment can also be done in the furnace. Degassing means whatever impurity is present in the material, that can be removed by providing some degassing agent like aluminum can be added, or by silicon can be added, like this. So with the help of this you can remove all the impurities present in the metal. And next you can see crucible furnace, correct? This is also a crucible furnace, and now you can see this is the electrical resistance heated crucible furnace. This is a ceramic crucible furnace, and around this you have a electric circuit, electric coil, induction coil. Obviously when you provide a heat, when you switch on the when you start supplying current, then because of induction huge amount of heat get liberated, and the heating rate is also very fast as compared to the gas combustion or diesel based furnaces. Is it right? So whatever metal you pour this in the crucible get melted very rapidly. Is it right? And after that, once it get melted, then with the by the tongue you can just remove this crucible, or by pouring by tilting this thing, we can remove the molten metal from the pouring spout. Okay, so this is the induction furnace. Is it right? Which is a part of crucible furnace, correct? Okay, once again you can see this is also induction furnace. In this we have a carbon electrode, correct? So induction furnace are used for all type of material. This is the biggest advantage of induction, and even heating rate is also very high. The chief advantage being heat source is isolated from the charge. Why? See, in this, as you see in the previous slide, the metal is completely separated from the heat source. Yes or no? So that's why the metal get pure, more pure metal we can obtain from this. Is it right? and contamination, chances of contamination from the burnt substance is also not there in the induction furnace. And the steering will also provide to the metal so that a uniform melting takes place. Is it right? The steering effect of the electric current would cause fluxes to be entertained in the melt if they are mixed along with the charges. Therefore, flux is generally added after switching off the current. Yes, after melting, when switch off the current, then we just add some flux so that it produces a slag which prevents the molten metal from the atmospheric contamination. And once it is prevented, then you can easily transport it from one location to another location. Is it right? Without any formation of slag or oxides of the metal. And since its melting rate is very fast, so it is generally used for making a small size casting and in a rapid production rate. Okay, and even induction furnace can also be used for permanent type of casting in which the pattern is frequently mold cavity is frequently available for the casting. So at a rapid rate it provides the supply of molten metal. And next, that is the last part of this metal casting process, that is casting defects. So let's see one by one. We have a blowhole defect. See, we have many types of defects. Let's I'm going to segregate these defects. First, you can say here, that is casting defect. Casting defect due to entrapment of gas. Entrapment of gas. Okay. So we have several defects like a blowhole defect, pinhole porosity defect, inclusion defect. Correct. So these are the basically uh, defects mainly produced due to the entrapment of gas. Okay. So let's see one by one. Suppose if I talk about blowhole. If I talk about blowhole, then obviously if you have a casting like this, and if permeability of the molding sand is not adequate, then some gases may trap at the interface between metal and the sand, and these gases may escape during solidification. Then we will get a cavity like this. So this cavity is called as blowhole defect. Is it right? So what is the main cause of this blowhole? Due to insufficient permeability. This is the main cause of this blowhole defect. Okay. In a convex surface, if we get a shallow cavity, then this is called as a blowhole defect. Next, we have a gas hole defect. In a gas hole defect, generally, due to when we have a very high turbulent flow of molten metal. Turbulent flow of molten metal, correct, and obviously lack of permeability. Sometimes gases may trap inside the casting. So these kind of defects is called as gas defects. Is it right? Now, what are the remedies of these defects? Then obviously the remedies is, if you provide proper permeability, improve permeability, improve permeability. Second one is provide more ventilation hole. vent hole so that the gases may easily escape from the casting. So, and of course, a proper getting design. These are the main region through which you can remove these defects. Okay, and now let's suppose if I talk about pinhole porosity defect. Pinhole porosity defect. Okay, pinhole porosity defects means it is mainly happen due to hydrogen embrittlement. Hydrogen embrittlement, and hydrogen embrittlement means see at a very elevated temperature, at a very high temperature, very high pouring temperature, when the metal come in contact with the moisture, then water vapor or moisture get disintegrated into hydrogen plus ion plus oxygen ion. Okay, and this integration, this is called dissociation of water vapor into hydrogen and oxygen molecules, and this oxygen react with carbon. It will produces either carbon dioxide or CO2. Is it right? Sorry, carbon monoxide or carbon dioxide. So it can be easily escaped, but the hydrogen gas may trapped inside. So let's suppose if this is a casting, so in this the hydrogen gas may trapped. Okay, hydrogen gas may trapped like this, and if it is trapped, then obviously after during solidification it escaped from the solid casting. Is it right? Like this, then it makes a very tiny hole. Is it right? A very tiny hole which is not even visible with the help of naked eye. So these tiny holes is called as pinhole porosity defect. Is it right? So this is the main cause of pinhole porosity defect, that is high pouring temperature. And how to remove this pinhole porosity defect? And it can be eliminated, it can be prevented by using optimum pouring temperature. Okay, optimum pouring temperature. Neither too high nor too low temperature will be used. Is it right? So that this water cannot dissociated. Is it right? And if it is not dissociated, then this types of defect may not produce. Okay. Next, inclusion defects. See here again, if very high turbulence takes place. Is it right? If your metal inclusion, suppose when you pour this molten metal, and if the getting system is not properly designed, if it is not properly designed, then the metal can flow at a very high speed. If the molten metal flow rate is very high, therefore turbulence will also be very high. And if turbulence is very high, then tendency of sand erosion will be more. If tendency of sand erosion will be more, then some sand particles may trap inside the molten metal. Is it right? So this types of, if impurities may trap inside this, then this is called as sand inclusion defect, or simply you can say inclusion defect. It is not necessary that sand get included. Some impurities may also included inside the metal. Is it right? That's why this is called as inclusion defects. And how to prevent this inclusion defects? Obviously by reducing the turbulent flow of the molten metal, or if you use optimum velocity of the molten metal, then we can able to reduce this. Next one is sand wash. So what is sand wash? Basically, see, if you can see here, this is a pouring basin. Okay. Now when you pour the molten metal from here, and if you directly turn this metal, then this region of the molten metal get molding sand get wash out. Okay, so this is called as sand wash. So why this sand wash takes place? Because of very rapid flow of molten metal. Is it right? uh, Rapid flow of or flow of molten metal at very high velocity. Very high velocity, the sand wash may takes place. Okay, so how we can prevent this? So directly, instead of turning molten metal directly, we just make a screw well at the bottom of the molten metal, bottom of the screw. Okay, and if you make like this, then obviously first molten metal goes down and then it moves up. So because of that, the velocity significantly reduces, and hence we prevent the sand wash. So this is called as sand wash. And why do we need to prevent this? Because if sand wash takes place, then obviously that sand particles may trap inside the molten metal and produces sand inclusion type defects. And next, sand fusion. Sand fusion, when sand fusion takes place, where the molten metal is very high. When molten metal temperature is very high and inappropriate sand selected, then this types of defects may produce. Why? Because see, when the molten metal temperature is very high, even it is more than the melting temperature of the sand, then sand particles may fuse like this. Sand particles may fuse with the metal. Is it right? Sand particles may fuse with the metal and produces some other, like if I talk about iron and silicon, then if silicon get melted and fused with the iron, then produces ferrite structure, which is very hard, and it is deposited over the surface of the casting. And after solidification, when we start machining, then due to the very hard surface produced by the ferrite structure, may causes a breakage of the tool. So reduce the machinability of the molten metal. Is it right? And next, a rat tail defect. So what is rat tail defect? Actually, if molding sand is not properly rammed, is it right? And when you pour the molten metal, when you pour the molten metal, then this molten metal easily can escape like this. So it is moving away from the mold cavity like a tail of the rat. So that's why this is called as rat tail defect. And what is the cause of this defect? The main cause of this defect is inappropriate ramming of the molten metal. Okay, inappropriate ramming of the inappropriate ramming of the molding sand causes less strength and less hardness of the molding sand. Hence, when you pour the molten metal, due to its metallostatic pressure, the metal can leak from the mold cavity. So this is called as rat and tail defect. Is it right? So this is all about defects, and you can see some more defects are also there, that like a scab defect. So scab is nothing but you have uh, if you have a hole on the flat surface, so this is called as scab. And if this scab is covered with a very thin narrow layer like this, then this is called as blister. Is it right? And drop, and obviously when, let's say this is a mold cavity, if the sand particles are not ramped properly and they don't have enough bonding strength, then obviously this sand particle may drop from here, and once it drops, then it makes a cavity somewhere here like this. Okay, so when you pour the molten metal inside this and allow for the solidification, then you will get a casting like this. Some raised portion we get at the top surface, and some depression we get at the bottom portion where the sand particles is situated. Okay, so this one is called as drop defect, and this is called as a dirt defect. Okay, next mold shift. Obviously uh, if the both cope and drag is not aligned to each other, then they will produce a mold shift defect. Okay, and similarly if the core print is not sufficient to hold the core, then when we pour the molten metal, then slightly the core can shift it from its original location, then this defect is called as core shift defect. And what is run out defect? So let's suppose if you want to make a casting like this, and when you start pouring molten metal from here, then obviously before reaching the molten metal at the extreme end, if it gets solidified, then this is called as a run out defect. Okay, metal penetration, if the molding sand is not properly rammed, is that right? And when you pour the molten metal somewhere here, then molten metal get penetrated in between the gap like this. So this is called as metal penetration between the molding sand, and it is mainly happen due to insufficient hardness of the molding sand. And similarly, hot tear, if I say, if you make a casting like this, then obviously this corner section is a critical zone where the surface area is very less, therefore heat transfer may also very slow, and because of this very slow heat transfer, the residual stresses may induce, and for removing of these residual stresses, here the crack formation takes place. So this is called as hot tear defect. Okay, cold set defect. Let's suppose if you have a two stream of the molten metal which is try to fill the mold cavity. One stream is flowing here and another stream is flowing here. And if both streams does not fuses properly, then this defect is called as cold set defect. And what is misrun defect? Already I told you this is misrun defect. This is not run out. Sorry, this is not run out defect. Run out. Run out defect is similar to a rat tail defect. Is it right? Run out defect is similar to a rat tail defect, and this is a misrun defect in which the molten metal does not reaches to extreme end. So this is called as misrun defect. Okay. So these are the different types of defects. Is it right? And mostly the cause of these defects is improper getting system design, improper permeability, improper ramming, insufficient strength and hardness of the molding sand. These are the overall cause of the defects, and how to eliminate this. Obviously, if you improve these things, then it can be easily prevented. Okay. So in this lecture, you can see the detail of a cupola furnace, induction furnace. Is it right? Their application and then defects in the metal casting process. Okay. And let's see some MCQ type questions. Which furnace is commonly used for melting cast iron in industries? So generally for cast iron, we use cupola furnace. Is it right? Which furnace offers precise temperature control and is suitable for the non-ferrous alloy? Then obviously induction furnace is used for this. It will produce a very precise temperature. In crucible furnace, the metal is melted. Crucible furnace metal is melted in direct contact with the fuel. Okay, there is no contact between the metal and the fuel. Which of the following is not a type of melting furnace? Cupola furnace, rotary furnace, crucible furnace, and Bessemer converter. Is it right? So rotary furnace is not a melting furnace. Okay. One major limitation of the cupola furnace is high cost cannot melt steel. This is the main reason. It cannot melt the steel. Is it right? This is the major disadvantage of cupola furnace. Okay. So this is all about metal casting process. So this first part of the first part of the manufacturing process of basic mechanical engineering is completed, and section of this unit will start in the next upcoming classes. Okay, so I hope you enjoy this watching this lecture. So thank you and good day to all of you guys.